Now, with chapter 3, this is going to be a little bit of an Algebra 2 repeat for you, with some harder stuff added in, of course. You know, they got to elevate it, bump it up. But what we're going to do in chapter 3 is we're going to do exponentials and their inverses, which are logs. Yes. So some of you guys were okay with logs last year? Yeah? Do you remember doing logs a little bit? Like log base 2 of 8? Do you know what the answer to that is? 3. Whoa. You're impressed. All right. So exponents and logs. So today we're just going to focus on lesson 3.1. We're not going to get into logs yet. They always start you off with exponents, okay? So we're going to do some exponential functions. Exponential. And then we're also going to throw in a new one at you, which is called logistic. Okay, logistic. And you will need your calculator for this lesson. I need mine. Let me go grab it. So let's first start off with our exponential functions. Okay, so let's recall what an exponential function is. So the definition of an exponential function that the book gives is it's a function, f of x equals, we have a times b to the x. Okay? Where a is our initial value, b is the base, b is not 1, by the way. Okay? So a is the initial value, b is the base, and that's just what an exponential function looks like. The exponent is the variable here. Okay? So what we did last time with the polynomials, all those exponents were all numbers. They were whole numbers. And so, yeah, the variable here is the exponent. Okay, so here we go. Number 1. We are going to identify an exponential function. ID, the exponential function. And we're going to say what the base is and what the initial value is. Identify the expo function. So it's kind of a yes or no question. Is it an exponential function? Yes. If so, what is the base? What is the initial value? Okay, here we go. Letter A. Start with a nice simple one. F of x equals 5 times 3 to the x. Okay, and make sure you realize that this is not 15 to the x. Okay, exponents come before multiplication. So it's 3 to the x and then times 5. So, yes, this is an exponential function. It looks exactly like I wrote up here, a times b to the x. 5 is the initial value. The initial value is found when x equals 0. Okay? And so if you plug in x equals 0, do you remember what 3 to the 0 was? It's 1. Yeah. Yeah, so you get 5 times 1. So the initial value is 5. I didn't have to do all that, right? Because we can see it right here. It's the initial value. And then the base is 3. So for this one, you start with 5, and then you basically are tripling each time. Okay? So 5, and then you would go 3 to the 1, so you get 15. 3 squared is 9 times 5, 45. So you're tripling all the way there. Okay, let's look at this one. Letter B. G of x equals 6x to the negative 4. Is that an exponential function? No. It has an exponent in it, but it's not an exponential function. This isn't even a polynomial. It's not. You know what this is? It's 6 over x to the 4th. That's just one of those rational functions that we did last chapter. But the answer is no. All right, another one. Letter C. How about h of x equals negative 2 times 1/2 to the x, and then I'm going to add plus 3. Now, this does not look like what I started with up above because of that plus 3 on the end, but that just means that it is an exponential function. It's just been shifted up 3. But it does affect the initial value. The initial value is not going to be negative 2. All right, so let's look at this. So this is yes. It's an exponential function. The base is 1/2. Okay. And then the initial value is very tempting to say it's negative 2, but it's not. it's really going to be -2 and then +3. So you get -2 times 1/2 to the 0 plus 3, which will give us +1. Okay? So when it's in that form a times b to the x, yeah, it's just that a, but because there was a +3 on the end, that changed it too. All right, let's do a couple more, 2 more. This one's kind of a fun one. M of x equals 5 times 6 to the pi. They're really trying to mess with you. Is that an exponential function? No. Do you know what that is? It's a constant. Right? Pi is a number. It's just 5 times 6 to a number. It's just a constant. So this would be no, not an exponential function. It's a constant. All right, last one. Letter E. P of x is equal to 7 times 2 to the -x. Now, this bothers some people, and they think, no, that's not an exponential function. It actually is. This is a yes. Okay? This is an exponential function. You can actually change this to get it into the way that they wrote it up above. If you did 7 times, and then 2 to the -x is 1 over 2 to the x, which is then equal to 7 times 1/2 to the x. You see that? Yeah. I used some algebra skills and got it to here, and everything was legit. And now I can say, okay, my initial value is what? 7, and the base is 1/2. Ooh, I just had a deja vu. That's cool.
Would you want us to like go through all those steps to get it in that form?
You might, yeah, you might want to, because if they ask you what the base is, it's hard to tell what the base is. But if you know that's 2 to the -x, so it's going to drop it down to 1/2, and that's the base, that's fine. You don't have to do all that. You can do that in your head. Yeah. Okay. Any questions so far? We're doing okay? Okay, here we go. Number 2, they have you do something like this just to remind you what exponents do. Yeah?
How exactly did you get 1 over 2 to the x to half to the x?
Okay, so then this is to the x right here, but then there's a 1 up top, so 1 to the x, yeah, is still, yeah. Yep, exactly. Okay, so we have f of x equals 2 to the x, and they're going to ask you to evaluate this for f of 4 and f of -3. Okay, just to remind you how to do this, and you can use your calculator. Okay, a lot of this chapter is going to be calculator. Some of it's not. We're going to do some graphing. That's not. We plug in 4, and so you get 2 to the 4, which is 2 times 2 times 2 times 2, which is 16. I know a lot of you guys can do that in your head. F of -3 would be 2 to the -3, which we never leave negative exponents in our answers. And so this is 1 over 2 cubed, which is 1/8. There you go. Okay, so very basic, nice little problem there. All right, now the next one's a little weird. It's something you haven't seen before. So let's do this one, number 3. All right, suppose that you have this table of values, and you have 2 different functions. You have g of x, and you have f of x. Okay? And they're going to give you some numbers for these, for some x values. So -2, -1, 0. Hold on. 1 and 2. And then they give us some values for g of x and then for f of x. So g of x, they say, is 4/9, and then 4/3, 4, 12, 36. Okay. And then f of x is 128, 32, 8, 2, and 1/2. And so what they want us to do is they want us to determine formulas for the exponential functions g and f for the given values. Okay? So we're going to find formulas for each of them. They're separate. Find formulas. All right. So here's where I like to start. I like to start finding my initial value. And the initial value always happens when x equals what? 0. Okay, so this right here, super important. So I'm going to do g of x first. So g of x is equal to 4 times. And now I have to figure out what the base is here. So what is it doing each time from 4 to 12, from 12 to 36? We're multiplying by what? 3. Even from 4/9 to 4/3 and 4/3 to 4, we're multiplying by 3 each time. So this would be 4 times 3 to the x. And if you want to make sure you're right, just try plugging 2 in. Okay? Plugging in 2 for x. We get 4 times 3 squared. 3 squared is 9 times 4. We get 36. So it's a really nice way to check, too. All right. F of x is a little bit more difficult, but we found our initial value. It's where x equals 0, so that's going to be 8. And then, is this one a little harder to figure out? Yeah? Yeah.
Is the 1/2 on the inaccurate? Because I actually just keep going because I think I'd try to give it away the answer.
Oh, okay. That's okay. Is it inaccurate?
Because I think that...
No, it's okay. Yeah,
Really?
let's look at it. Okay, so what do you think is happening each time here? What are we doing? We're multiplying by 1/4. You could think of you're dividing by 4, okay? But dividing by 4 is the same thing as multiplying by 1/4. You want to get like a multiplying thing going. So when you go from 2 to 1/2, 2 times 1/4 is 1/2. Yeah, so we're good. Yep, so then I would write 1/4 and then x. Okay, another way to do that would have been to do what? You could have done exactly 4 to the negative x. That would have worked out just fine too. Yeah, but this is fine right here. I like that. Okay.
Would you prefer the fraction rather than negative x?
Yeah, I would. I prefer that. So, all right, let's go on to the next part, part B. Part B, this is all kind of review too from Algebra 2. We're going to do some growth and decay problems. Okay? Yep, exponential growth and exponential decay. Okay, so a lot of times you think, okay, everything's linear. You know, we're on this linear thing. But a lot of times population, half-life, you know, things that actually show up in real life are not linear. They're exponential. And so we have to have an exponential function for this. Okay, so let's do both of them. Let's look at an exponential growth. Okay. So here's our basic parent function. It looks like this. You have a point here at 0, 1. And you have an asymptote that goes through y equals 0 is our asymptote. Okay? And your graph will look like this. It'll go right along this asymptote, and then it shoots up pretty quickly because it's an exponential growth, so depending on how fast it's growing. Okay? But that's what it's like. It's not linear. Okay? It starts off pretty low, and then it goes pretty high. I'm sure you recognize this from last year. Let's say this is 1. So that would be, this would be the point 1, comma, b. If you had just your basic f of x equals a times b to the x. 1 should be ab. I think they said a was 1 here. Okay. And then a decay would then look like this. Here's your graph, and it's still going to go through this point of 0, 1. You're still having an asymptote at y equals 0. Okay, this is your parent function, so these can get shifted and stuff, and we're going to do that in a little bit. And then here's your graph. It starts off, and then it goes right next to your asymptote there. Okay? All right, so let's talk about the domain and the range and all that stuff, because that's what we always do, right? So the domain for just your basic parent function graph is going to be all real numbers. And that's going to be true for all exponential functions, okay? You can plug anything you want to in for x. You can plug decimals in, negatives, it doesn't matter. You can take anything to the 1/2 or to the negative 30 or whatever, it doesn't matter. Now the range, though, is y is greater than 0. There's an asymptote at 0, so everything above that works, okay? And these are going to change when we shift and do our reflections and stuff like that. Okay. The other thing to note that this is a continuous graph. There are no breaks, no holes, no jumps, nothing weird going on. All right. They do talk about limits again. Okay. They say the limit as x goes out to infinity is going to be 0. So as you work your way out this way, our y is getting closer and closer to 0. And then the other way, that's for this one right here. The other way, the limit as x goes to negative infinity for a decay problem would go up to infinity. So the y is going up. And it's the reverse for growth. But you know what? I'm not going to really focus on that too much. I did take it off the test. So, okay, so here we go. Number 4. Number 4. We are going to take y equals 10 times 1/2 to the x. And we're going to graph this. And we're going to say whether this is exponential growth or decay. So to graph this, if you don't have a calculator, if it's one of those problems in your book that's grayed out, you're not allowed to use a calculator, you can give yourself a little t-chart. Okay. So my initial value is when x equals 0. So in this case, my initial value would be 10. If I plug in x equals 1/2, or I'm sorry, 1, I get 1/2 to the 1 times 10, which gives me 5. Okay. If I plug in 2, I'm getting half of 5, right, which is 2.5. If I go the other way, and let's plug in -1. -1 would go, if you had to plug that in by yourself, and you did 10 times 1/2 to the -1, that's what? Can you do that in your head? 20. 1/2, that gets flipped, right? Because this is to the -1, so you get 20 there. All right, so let's plot some points. So I have -1, and this is what I'm going to do. I'm going to go 10, 20. These numbers get really big as you go out. Okay? So -1, I have positive 20. 0, I got 10. At 1, we got 5. And then at 2, we get 2.5. And look how quickly that goes, huh? And so it goes like this. Draw a nice smooth curve through it. But then, ooh, I kind of missed. But then do not cross the x-axis. And make sure that you do include your asymptote when you draw. Okay, so is this growth or decay? That's what they're going to ask you too. This would be decay. And you can probably tell before you even graph it, right? Its decay factor is 1/2. It'd be like if you had $100,000 and you wanted to spend half your money each week, right? That'd be really fun, but probably not a good idea. All right, let's do some graphs by hand now. We just did one, but now we're going to have some like shifting and parent functions and all that stuff. So, graphs. We got a lot. All right, you're probably wondering how long is this going to last. We got graphs, and then we have logistic functions, which are on our calculator, and that's it. Okay? All right, so graphs, here we go. We're going to start with y equals b to the x. That's going to be our parent function. That's the ones I graphed earlier. They say a equals 1, so they just have y equals b to the x. So let me show you what's going to happen when you do some shiftings and reflectings and stuff. If you have y equals b to the x plus 1, okay, what would happen is you would shift this 1 to the, does anyone know? 1 to the left. This would take your graph, your parent function, and it would shift it 1 to the left. Now, if I have y equals b to the x and then plus 1, see how different that is? The one's not with the x, the one's down here. This is going to shift this thing what? Perfect, 1 up. Okay? So look for that. If it's in the exponent with the x, that's a shift of left and right. If it's down, with the stuff, then it's up and down. And then also, if you have y equals b to the negative x and y equals negative b to the x, those are going to be different reflections too. Y equals b to the negative x, okay, that's taking all my negatives and making them, or all my positives and making them negatives. that's going to be a reflection over the y-axis. And then a negative b, that's going to be a reflection over the x-axis. There you go. Same rules? Yep, I know. Same rules as all the times. Now the only thing that's really kind of tricky on here that people mess up is they start from the origin on accident, and you shouldn't. Okay? Remember our y equals b to the x? This is the point that we're going to be moving. Okay? There's an asymptote here, and we're really looking at it like that, and we got to move that thing. Okay? So be careful. All right, what am I on? 5? 5. Number 5. Let's do one now. Let's do one that has, a bunch in it. Yeah?
So when you're flipping over the x-axis, you mean in b times -1, not negative
Right.
b to the x. Because
Right.
that'll do that.
Yes, yeah. Yeah, the negative's on the outside of the b.
Okay.
Exactly. Okay, so let's do y equals 2 to the x plus 1 minus 3. And so what we're going to do is we're going to take our parent function, which is y equals 2 to the x. Now that 2, that base there, that matters to us somewhat. I'll show you what I mean. When I graph this, I always like to kind of graph my parent function first. So I'm going to graph that in green. My parent function starts right here at 0, 1. And I always like to get a second point. So if I go over here to 1, I'm up here at 2. Okay? If this was 3 to the x, I would be up here at 3. So it just makes it steeper. It's the same shape though. So here's my parent function. Okay? I start with this, and I start with my asymptote. And now I'm going to take that, and I'm going to shift this thing. I'm going to go 1 to the right and 3 down. Okay? So I'm going to take this point right there, that point, and shift that. I'm going to shift it 1 to the, oops, I said right, didn't I? I know, some of you guys were quiet on that, but some of you guys looked at me like, nope. You can speak up, it's okay. All right, 1 to the left, so let's go this way, and then 3 down. 1, 2, 3. So there's that point that I have right there. Now don't forget, you do also need to shift the asymptote. The asymptote, shifting it left and right doesn't matter, okay? It's a straight line. But it also gets shifted down 3. So 1, 2, 3. So here's my asymptote, okay? We can also do this point right here, which was 1, 1, 2, 3, right there. Okay, so here comes my actual graph. There we go. Okay. And then they're going to ask for some things on this. They will ask you what the domain, what the range is. Okay. Domain's the easy one. Domain's all real numbers. And the range would be, on this one, it would be what? Y is greater than -3. Perfect. Okay. They could ask for the Y-intercept. The Y-intercept is to just let x equal 0. Okay. So we can see the Y-intercept on our graph too. But if we let x equal 0, we get 2 to the 1 minus 3. So our Y-intercept is -1, which there it is. The X-intercept's a little trickier to do. The X-intercept is to let y equal 0. And so this one, we're not really going to solve this yet. You add 3 to the other side, and then we stop and we go, If I plug in 0, I get 3 equals 2. If I plug in 1, I get 3 equals 4. So it's in between 0 and 1. I actually kind of didn't graph it right. It should be between here. It should be a little bit steeper. But we know how to solve this with logs, but we're not there yet. So you don't need to worry about it, okay? So we'll just say that it's somewhere between 0 and 1. We're not going to do it yet.
Will they ask for that?
I don't think so. Yeah. If they do, just know that, we're going to wait on that until we get to actual doing logs, okay? All right. And then we also have E. Remember E? E's a number. So we have, if we wanted to, we could graph y equals e to the x. Let's go ahead and do that one on our calculator. Okay? So get your calculator out. if you remember what E is an irrational number. It's an irrational number. It's just like pi. It cannot be written as a fraction. Okay, there's some fractions that are close to it. You might think it's it, but it cannot be written as a fraction. Write that on your paper. That's important. People thought that pi was what, 22/7? It's not. It's a good approximation, but it's not. E, you know what E is? E is, it's the limit as x goes out to infinity for 1 plus 1 over x to the x. It shows up a lot. It shows up especially in exponential functions and stuff. So if you were to graph this right here on your calculator, it would have a horizontal asymptote of E. And E, do you know what number that is? If you ever wanted to know, you could go like this and go E and hit enter, and it'll tell you what it is on your calculator, approximately. It's approximately 2.71828, and then it looks like it repeats because it says 1828, but then it does a bunch of different numbers after that. So, okay, irrational number. So let's go ahead and let's graph y equals e to the x on our calculator. So here we go. I like to use, E's in two separate places on your calculator. I don't know which one you prefer. E is above the division sign. It's just E. But then e to the x is over here above the natural log. So I use that one a lot more. So I go e to the x, hit zoom 6, and it's just going to look like a basic exponential function. Okay, you can hit trace, plug in some numbers. Just looks like this. The base is 2.718, so it's between 2 and 3. So it's more than doubling, but less than tripling each time. Okay, so that's just a basic sketch of E. All right, last part. Whew, we're doing great on time. Okay, this next one's kind of fun. I like to do these on my calculator too. They're different. This is called a logistic function. I know the word log is in there, but it's not a log function. It's different. Logistic function. Okay. And do they give you the basic logistic function? They do. Here's basic logistic function. It looks like this. F of x is equal to 1 over 1 plus e to the negative x. Okay? It's a bit complicated of a function. The parent function of it looks like this. What happens is you're going to get two asymptotes on this function. Yeah. You get one here, and then you get one here. And what happens is it looks like a basic exponential growth, like an exponential function, but then it tapers off. Okay? And it's a really good model to use because, you know, if you're talking about population, is it ever going to go to infinity? No. No. It tapers off a lot of times. Okay? And you can't have so many bears in a place or else the bears are just going to, you know, they're not going to keep going to infinity. They do this with like bear population stuff. It's really cute. All right, so here we go. Let me go ahead. Oh, and this right here for your basic parent function, this is y equals 1, and this is y equals 0. So it stays between 0 and 1 when you graph it. So let's graph one, a different one. Number 7. Do I have 2 of these? I have 2. If you get it on the first one, we will be okay. All right, here we go. F of x is equal to 8 over 1 plus 3 times 0.7 to the x. Okay, so they changed a bunch of numbers on you. What we're going to do is we're going to graph this on our calculator, and we're going to sketch a graph, and then we're going to find some things. We're going to find the Y-intercept, and we're also going to find the horizontal asymptotes. Okay? All right, so let's put this in our calculator. You got to be careful. You're going to need some parentheses, okay? So we'll go with, here, put it right here, y equals, can you see that? Yeah. 8 divided by parentheses, 1 plus 3 times, you don't need the parentheses there, 0.7 to the x, because your calculator knows that you're going to do correct order of operations. Let's hit zoom 6. See what it does. Okay, looks exponential, and then it just kind of fizzles out. It's pretty cool, huh? You like it? All right, so here's a couple of things. The Y-intercept, yeah, you have it graphed. You can hit trace, plug in x equals 0, so your Y-intercept is 2. Okay. Y-intercept is 2. Y-intercept is basically just 8 over 1 plus 3. Okay, 8 over 4, 2. The horizontal asymptotes, there's 2 of them. There's one at y equals 0. Okay, I don't know if you caught that. And then there's one above here, and we're going to find out what that one is. We're going to go like this, and like that. All right, what do you think that one is? Does anyone figure it out? You go over to the table, and you can scroll out. Oh, wow. Hold on. Let me set my table at 0. So I start here, and when x is 5, y is 5.3, then it's 5.9, 6.8, 7.1, and then check out that 7.99999. And then my calculator actually failed. It lies to me. It says it's 8, but it's not. Okay. So the horizontal asymptote right here would be y equals 8. Ooh, I see 8 in my equation somewhere. Do you see 8? Is that number on top? Yeah, that's what it's going to be.
So why did your calculator say that it was 8?
Because it gets so close to it that the calculator can't give me any more decimals. Yeah, that it just says, nah, it's 8. I don't know. Do the new calculators do that? Yeah, maybe? No?
Sure.
Yeah, they do.
They might be a little slower.
They're slower. They're a little bit slower, yeah. So let's look at number 8 real quick, and without using our calculator. Okay? Let's do g of x equals 20 over 1 plus 2, e to the negative 3x. This one's complicated. Maybe we do need to use our calculator, but we'll see. All right, we're going to find the y-intercept. Actually, I want to graph this one on our calculator. But you can find the y-intercept without graphing it. Okay? To find the y-intercept, you let x equal 0. And so you would get 20 over 1 plus 2 times 1. E to the negative 3x would be e to the 0, which is 1. Okay? So you get 20 over 3, 20/3, kind of a gross y-intercept. You can tell just by looking at this logistic function now that your asymptotes, like according to the last one when you got y equals 0, and then this one would also be, what do you think it is? 20. Perfect. Y equals 20. This is that constant up top. Okay? So let's see what that negative 3 to the x does to this thing. I'm not sure what this looks like, so let's graph it on our calculator. So we got 20 divided by parentheses 1 plus 2 e to the negative 3x, and then close parentheses. I do want to change my window because I do know that it's going to be, an asymptote at 20, horizontal asymptote. So I'm going to go to 30 here and just see what happens. All right, basically the same thing. Look at that. Look how flat that is. That's so funny. It's the same thing, pretty much. It just, it happens very fast. It increases and then levels off very quickly. So you have one at 20 and you have one at 0. Okay, I like those. Those are fun.